Yeah? I'll start the next lesson?
Yeah.
Okay, I'm not so sure about this. Have I got everyone? I do.
Yeah.
Good break? So,
Stayed in Dublin, so we had 2 storms.
yeah, it was raining a lot, wasn't it? Yeah. I've been wanting to cut the grass for like over a week now, but it's too wet.
Yeah.
So it hasn't stopped raining. Maybe I'll get to this weekend. Okay. Electric field potential. Can you all see okay? Yeah. So, well actually, you know, since it's been a week, maybe it's even worth just quickly recapping what we did last time, because we were at the start of a new chapter. What did we do? Oh, come on, don't be a jerk. Sorry, I know I can't really open 2 at the same time because it messes up. We'll just quickly run through what we did before the break. So what did we have a look at before we took our break? Yes. We talked about electric charge, that's fine. We talked about negative and positive, that's fine. We talked about a field, that's fine. And then we talked about charge, it's fine. We gave you values, yeah.
Field strength.
And then we talked about field strength.
Yeah, and formulas.
Yeah, electric field strength and the formula and the units and examples. And then we looked at point, sphere, parallel plates, dipole, point, sphere and parallel plates. And then we did equipotential, good, okay. And then we did plates. Actually, we did a lot.
Yeah.
Then we did a point. And then we did some more examples. Yeah, okay. So we actually did an awful lot. So let's start the next one. So we did something kind of like this in mechanics. Anyways, we'll get started. So you remember from mechanics, of course, when a particle is above the ground, it has potential energy, obviously. And in fact, I hope you remember the formula. It's mgh. Why is that? Well, because there's a force acting on it, which could cause an acceleration, which could increase the speed, and therefore its kinetic energy. The KE must have come from somewhere, so it had PE at the start. So I'll give you an example. Like, I'm holding this above the ground. It has potential. Why does it have potential? Because now it has kinetic. That kinetic must have came from somewhere. It came from potential. Why does it have kinetic? Because it's accelerating. Why is it accelerating? Because it's falling because there's a force. So the point is, if there's a force that could act, then we say that's potential energy. Okay, so like even like, I don't know, if I'm trying to think of an example. Yeah, like if I'm holding this here and I'm pushing down on this here, I'm actually putting potential energy in it because I'm applying a force. And you can release this energy and make it come kinetic if I do something like this. So, do you get what I'm saying? Like, the force is what gives it the potential energy because there's a force present. It's the same with the rubber band. You know, if you pull this, it has a potential energy stored in it because of the force of the spring ready to accelerate it. Do we get the idea? Yeah, it's okay? Yeah. So, when a charged particle is between 2 parallel plates, there's a force, just like gravity. And therefore it must have potential energy. So, by doing a little bit of comparison, we can work out the formula. So, I'd like you to write this down, or draw this. I'll split the page in half. Okay, so we have our 2 plates. And I'll put my charged particle here. I'll call it small q. And I'll say it has a positive charge. Okay? And then this here is negative, and this here is positive. Oh, and just so you're not confused, there's no gravity here, okay? We're just, imagine it's in space or something, no gravity. So, what direction is the force here? It'll be downwards, won't it? It'll move down. Let's call this distance here, I don't know, let's just call it D. Okay, and then this is a force here. Right, how big is this force? Do you remember the formula?
1/4 pi.
No, not that one. Not that one. Well, F equals EQ. Yeah? Remember that? Now, what is the formula for the E here? For parallel plates?
Voltage over distance.
Yeah. V over D Q. Yes?
Yeah.
Do you remember this? Or has it been too long?
No.
Do you have one too many drinks during your break? Okay, let me see. What am I saying here? What? Oh yeah, sorry. Actually, do you know what? I won't write the V. I won't write that in just yet. I just want to switch back to the example here. So imagine you have a mass here, m, above the ground. Again, we'll call this height here h. There's a force acting downwards here, isn't there? And what's the force here equal to? mg. Okay. And this has a potential energy. What's the potential energy equal to here? mgh then. Now, I want you to compare the two pictures. They're actually quite similar, aren't they? They both have a height, right? They both have a downward force here. Yes. If you look at the formula for the force, this m here is something to do with the particle, and this q here is something to do with the particle. So actually, maybe I should even write it like this: Q E. Yes?
Yeah.
So here, if I was to guess the potential energy formula here, by drawing a comparison between the two pictures, the Q is a little bit like what here?
Mass.
It's a little bit like the mass, isn't it? So here we have mgh. So instead of the m, what do you think it would be? Q. Okay. Now the E here is a little bit like the G, so maybe it's QE here, and the D here is a little bit like the H there. Now, I can give you another way to prove it as well without a direct comparison, but you kind of get the idea as well. Just before you do that, before you write that down, let me just give you the other quick way to compare this. I don't know if you remember this from semester 1, but imagine the particles on the ground here. Does it have kinetic or potential? No, it has nothing. I raise it up to the top here, and what type of energy does it have here? Potential. Where did that potential come from? Yeah, by lifting it. It came from the work done to lift it. And what's the formula for work? Force times distance. And what's the distance here? It's d. And what's the force here? Well, the force pulling it up has to cancel the force pulling it down. So F, we said, is QE. So I've given you kind of 3 pictures here, but they're all kind of the same picture. You end up with this result, that the potential energy is QED.
But doesn't that disregard the repulsion force?
No, the two are working together.
So you consider them as one?
Yeah. I mean, Zach, the thing is,
Like, where is E? E is not constant, is it? In
no, so this here is when it's raised to the top. I think the E actually is kind of constant.
in a parallel plate.
Yeah. Yeah.
Because surely, like, if it was closer to the repulsion would get more and the attraction would get less, and they
Yeah,
balance
so
each
that's why I think you can consider it a
Yeah.
constant. Is this okay, this formula? So when you put your little charge in between the plates, it suddenly gains a potential energy. Yeah? Is it okay? Can you all understand what I'm saying? It's very similar to what we did in mechanics with the MGH. Instead of MGH, it's QED. The Q is acting like the M and the E is acting like the G. Now that's actually important. The E is acting like the G. We'll return to that later.
How does QED give joules?
Oh, okay. What's the unit for Q? Coulombs.
Coulombs.
E is newtons per newtons per coulomb, isn't it?
Yeah.
And D?
Meters. Oh.
Just like that. Just like that. Physics is funny like that, isn't it?
Yeah, it's newtons per coulomb. Why did I think it was? Oh, I was thinking of the I don't know how to pronounce this Greek letter.
Oh, theta.
No.
Oh, the E one.
Epsilon.
Epsilon. Constant.
Yeah.
That
The
one
different
is
one. Can I continue?
Coulomb squared times per Newton meter squared.
Ah, yes, that's quite a different one. Can I continue? Yeah?
Yeah.
So, the potential energy, you have the formula, is QEH. I used H in this formula, I'm sorry. And this is more commonly written as QV, because what you can do now is use the formula that E equals V over D. So then you get potential energy will be equal to Q V over D times D. Yeah, so you get P E equals Q, Q V, which is even simpler formula. It's just the charge multiplied by the voltage. Somehow I managed to turn the computer on, like, I don't know, telekinetically or something. I don't know how I did that. It just turned itself
Maybe
on.
it was just sleeping and you pressed the.
Yeah.
Maybe, but I was here.
My computer or something.
Okay, do you have that? QV? Yeah? Okay, now. Oh yes, I hope you know this from chemistry. The cathode is the negative plate. And what's the other one called?
Anode.
Yeah. Is these words you've done in
Cation and I.
Yeah, yeah.
Wait, why is one of the Q small and one Q?
Oh, I'm being inconsistent. I'm sorry. I'm a horrible teacher. I should be consistent with my Q's. The problem is actually, seriously, I haven't decided if I want to use small or big Q. So,
Does it mean
What
something
do they
big,
use
big
in
or
the
small?
UK? It's just convention.
they use both. They use a small Q when it's a small charge and a big Q when it's a big charge. I'm serious, so I don't know. Whatever you want.
Or you just change all of them.
Yeah, I should change all of them, shouldn't I?
Or something. Just use random letters.
Continue?
Yeah.
Do you know the word cathode and anode? Do you need to write them down?
I know cat is nate because they're such
That's how I remember it too, actually.
What? Cat is negative. Oh.
Okay, continue?
Yeah.
Yep. So, next now. Remember, if potential energy is positive, then we say it has potential energy. If it's zero, what do we say?
There's no, like, has no.
Oh yeah, well thank you, Captain Obvious.
Yeah.
What's the meaning of potential energy equal to zero?
It's on the ground.
In this context,
It's at the.
we have a special word to describe it if there's no potential energy.
Give us a hint.
Well, he did it in mechanics, so that was semester 1. Would have been around about week, I don't know, 2 or 3.
Stationary.
Ah, no,
static.
no, you forgot. If the potential energy is zero, we say the particle is free. Remember? And then what if the potential energy is negative?
It's in the
Something well.
I remember that.
Yeah, potential well is in it, yeah. Yeah, we say it's trapped in a potential well.
How is that possible
Well, it's
Parallel
under
plates.
as well.
In parallel plates,
It's not possible.
it's not possible to be trapped because you're either with potential energy or free. However, we will see trapped when we're talking about orbits around nuclei, which of course you're familiar with from chemistry. We say the electrons are trapped in orbits. I think you forgot these and you should write them down. What do you think? Yes.
How much voltage?
Nothing. They're never gonna make it.
He'll make it. He'll make it. Watch. See?
Well, it's the first time he does. That's alright.
Okay, you got that? Guys, you got that?
Yeah.
Continue. Zach? Yeah? Okay. Now, the conservation of energy implies that the initial energy must equal the final energy. So, if we think about the example here with the plate, here it has potential energy, and then here it'll have kinetic energy. And so, it must be that they're equal. You know this, of course. So you can say that QV must equal a half small v squared. So we get, well, you know this already. So since we have PE equals QE and Q is so small, we can, oh, actually I didn't write it down, sorry. So I didn't write it down, but it is useful to use this for, for parallel plates. Now just be careful, this is only for parallel plates when you have a picture like this. And it starts here with a potential energy and finishes here with a kinetic energy. Okay? This is useful. Because often we can know the Q and the V. So this can give us the M if we know the speed, or the speed if we know the M. Okay, do you want to write that down, Zach? Just here. Have you got that? Yeah? Continue? Yeah? So, usually the Q is really, really small, you know, like an electron or whatever. And so often we use a different unit to measure energy. So, if we were to look at this formula here, yeah, we could use joules. But here's the problem. The V can be, you know, big enough. It could be like, for example, 10 volts. But the Q is usually, what's it like, 10 to the minus 19 or something. And this is just too small of a unit. I mean, 10 to the minus 19, that's not even nano. Nano is minus 9. So we use this new unit to measure very small energies called the electron volt. This is measuring a very small energy. And the electron volt is defined as the energy gained when one electron is in a field of 1 volt. So before you write that down, let me just draw a picture, okay? Here is 1 electron, and here is the negative plate, and here is the positive plate. And we'll say that the voltage here is 1 volt. So according to the formula, PE is equal to QB. What's the V in this definition? 1. So that's just equal to E. So what we're basically saying is that E joules, which is a small number, we call that 1 electron volt. Okay? So on your calculator, if you want to convert to electron volts, you just divide by that E constant for charge, right? Now, let's go back to the proper definition. Here you go. You can write this down. Okay, have you got that? Yeah? Yeah, we all got that? Is that okay? So, do any of you watch sci-fi? Any sci-fi shows? No sci-fi?
Depends on the definition of sci-fi.
Well, what would you consider sci-fi?
Some say it's sci-fi, but it's not.
What is? I'll tell you if it's sci-fi. What is it that you watch? Rick and Morty? Maybe not really sci-fi.
Star Trek.
Star Trek is definitely sci-fi.
Oh.
Interstellar, yeah.
Yeah.
Or even comic shows like The Flash.
Those are.
I consider The Flash kind of sci-fi.
Then
Kind of sci-fi. The reason I say this is because a very, very, very common mistake in sci-fi, you'll notice it, is to sound more technical, they'll measure energy using electron volts. So they'll say something like, oh, this whatever it is thing has 10 mega electron volts of energy in it, so you have to be careful. But they don't really realize that electron volt is a tiny amount of energy. So even 10 mega electron volts is
less than a joule.
less than a joule. Yeah. So I noticed this in The Flash. I also noticed this in Star Trek as well. You know, like twice I saw them saying like, oh, don't touch that panel. There's 10 mega electron volts running through it. I'm like, yeah, okay. So anyways, electron volt sounds cool, but it's actually a tiny unit of energy. Okay, it's absolutely tiny. You'll not feel it. Here's a very simple one for you to demonstrate this. Using your calculator, give me 1 electron volt in joules. So what did you get? It should be something like, what is it, 1.67, is it? Or?
1.602 times 10 to the minus 19.
Yeah, that's it. 10 to the minus 19 joules. Yep.
It's the Coulomb charge.
Exactly, yeah. Okay, a little bit different now. Convert 1 joule into electron volts.
We just go 1 over.
Yeah, correct.
6.24 times 10 to the 18.
Yep.
Electron volts.
Yep. Okay, continue. Okay. 2 plates of separated distance of 2 centimeters. Potential difference of 500 volts. An electron leaves the negatively charged plate and accelerates towards the positive plate. How fast will it hit the positive plate? So, I'll just draw the picture. You've got the negative plate here, which is the cathode, and the positive plate here, which is the anode. And a little electron leaves the plate and smashes down here. This is 500 volts.
Charge.
And then the distance here is 2 centimeters.
You don't really need that.
Do you know, you're right actually. Oh wait, hang on. No, I think you could do it without the 2 centimeters. I think I gave the 2 centimeters because you could use UVATS perhaps. Anyways,
What is the charge then?
it's an electron.
Oh.
So, I want you to tell me what the V is here, please. See what you get.
The speed.
Yeah.
So, roots. Is this ME the mass of the electron?
Yes.
Number 3.
You got it? Lynn? No? You need to use the formula I gave you earlier. The QV equals a half mv squared.
I got a massive answer.
Yeah, it should be going pretty fast.
Like super fast.
Like the flash fast.
Like 13,262,051
Yeah.
meters per second.
Could be. Let's see. Let's have a look. So, the potential energy here must equal the kinetic energy here. So that means QV equals a half mv squared. So that means the small v will equal 2QV over m, root of. Yeah. So let's see. You can actually use your calculator here. You have the Q, it's constant E on the calculator.
Yeah, shift
The V is 500, and the M is the mass of the electron, which is constant 3 on the calculator. So it's basically square root 1000 E over ME. And what did you get for that, Zach?
I'm just doing it again.
Okay.
Check. Syntax error. Yeah, what? 13,260.
Did you take the root?
Yeah.
Okay. So
it's 1.1234567. So 13.3 to the power 6 is mega.
6, is it?
Yeah.
Is that right? Is it? Are you sure it's 6?
Yeah.
Mhm.
1, 2, 3, 4, 5, 6. Yeah.
Interesting. So this actually accidentally is impossible.
This is faster than the speed of light.
Yeah. So
You changed
I think the voltage, yeah, is too big. It's not a possible number. We try to obey the speed of light, so you can't be going faster than the speed of light. So it's not a real. No, the speed of light is 3 times. Oh no, you're right. It's 3 times 10 to the 8, isn't it?
Yeah.
Oh, we're all right. We're all right. Actually, Zach, could you just divide this by 3 times 10 to the 8? I'm just curious what it would be as a percentage.
0.044.
0.044 C.
Yeah.
Ah, we're all right then. That's only 4% of C.
Not even close.
No, it's still pretty fast though. All right. Is that okay? Yeah. These are called, you would have seen this perhaps in chemistry when you did, what's it called?
Redox reactions.
No, what's the machine called? The spectrometer. You studied how the spectrometer works. So the first stage is what you heat it up into a gas, isn't it?
Yeah.
Yeah.
And then you bombard it with particles. What do you bombard it with?
Electrons.
Electrons. This is to give it a charge.
To ionize it.
To ionize it, yeah. And then you put it into an electric field.
You accelerate it.
Accelerate it, yeah. So that's actually what we're looking at today, that stage of the process. What you have is, what charge does it usually have after you bombard it with the electrons? It's a positive charge, isn't it? Could you? Yeah. So your gas now has a positive charge, and then it enters an electric field. Obviously, you'll have to put a little hole in the plate, so you can fit it through. So there'll be like a little hole here, and then there'll be a little hole here. And that's this plate would be the positive plate, and this would be the negative plate, and there's an electric field here. And what happens is when the gas enters through here, it will accelerate, and you can actually calculate the speed because the kinetic energy here should equal potential energy here. And you can see that potentially, like in the last example, you can get really high speeds. Really high speeds. It's not too difficult to make 500 volts. You know, it's not too difficult. So you can actually get quite a high speed. Now, we'll do this in a later lesson, but does anyone remember what the next stage in the spectrometer machine is after the electric field?
The electromagnetic field.
Yeah, or just I call it the magnetic field. Now, we haven't studied magnetic fields yet, but since you did this in chemistry, what is the purpose of the magnetic field? So the purpose of the electric field is to accelerate it up to a high speed. What's the purpose of the magnetic field?
To deflect them by mass.
Yeah.
That's the charge.
It will swing around on a circle.
Particles would get.
Yeah. We are actually going to calculate later the deflection because we actually need it for the exam. We'll be able to work out, for example, you could measure the deflection and work out the mass to charge ratio by how much deflection there is. Because I think probably in the chemistry class you were just told, oh, a bigger deflection means a bigger mass to charge the ratio. We'll actually calculate it. We'll say if the deflection is this, then the mass to charge ratio is this. Okay? Yeah?
But doesn't the mass to charge ratio also depend on what kind of atom it is?
Not too much. Just depends on the mass of the charge. That's all.
Because some ions are heavier, but the mass to charge ratio will be like half because they have.
Don't know. Sounds like a chemistry problem to me. I don't know. I don't think about it too much. I just care about the equations. So I know they work. That's enough for me. And lastly, maybe you don't, but if you had grandparents, perhaps might have this at home. Your grandparents or even just parents might have a particle accelerator at home.
Oh yeah, just like the one in Switzerland.
No, well, just like not quite like the one in Switzerland. Does anybody know what device in your parents' or grandparents' home is like this. That's a particle accelerator. This is a particle accelerator. There's actually one at home, but not maybe in your home, maybe in your grandparents' home. Does anyone know? No. For a particle accelerator, I'll tell you, it's the old TVs.
Oh yeah, I haven't seen.
So what happens with the old TVs is a little electron is released, and then it travels between your two plates, and it accelerates. And then the electron hits the screen and causes a fluorescence. You know, the old big TVs.
That's why when you put a magnet.
Yeah, that's why if you put the magnet to it, you can change the image. Yeah. So the old TVs are actually electron accelerators. That's why they're so big. They fire an electron at the screen, accelerating an electric field. Which sounds cooler than an LCD, doesn't it? Yeah. Yeah. So, I guess you could say it's an improvement, but it's not as exciting though.
There's some TVs that are like wallpaper thin. It's like crazy.
Yeah, this is like new nanomaterial technology. I still can't believe that you can have phones that fold.
And then you have
The screen.
What's it called? The 2 nanometer or something
Z
like that.
Flip.
I
Like
don't-
Samsung Galaxy.
I don't know how they do it. It's quite amazing.
I don't know how the glass works.
Yeah.
I
Amazing.
bet it's glass. It is glass.
But do you
It's a
really need your
special
phone
kind
to
of-
fold?
That's what I'm saying. It's more of a gimmick.
Like really? I think my life can go quite well without having my screen fold.
Well, maybe not for phones, but for
Yeah.
other types of displays and stuff like that you can put in surfaces that will move.
Maybe.
You know, but like not the technology not applied for phones, but for other things.
Maybe something useful to something else, yeah. Now, let's see. We have one more example here. Ah, yes, okay. Very similar. An electron enters a field with a potential difference of 10 kilovolts. That's a huge electric field that will be produced. The electron accelerates across the field until it hits 3 protons at rest on the positive plate. The electrons bind. So it's very similar actually to what's happening here. The only difference in my story is,
Mass is changing.
yeah, the electron will hit 3 protons here. The electron will bind to the 3 protons and they move off together.
Mass, yeah.
So my question is, how fast do they move off?
Oh, it's a fundamental question.
Off you go.
10 kilovolts? Are you sure we won't get an answer that's faster than the speed of light?
Yeah, I'm going to take that chance.
Well, it's 4% at 500.
So it's 20 times bigger. Cutting it close. Might be alright. doing? Get an answer?
Mm. Got to be quite small. First.
Yeah, I think it's because the electron is so small when it hits the 3 protons. We'll have a look. So, we can use our formula. QV equals a half V squared. Yeah. The Q, well, what did we say the V was? 10,000, was it? So that's 10 to the 4. Yeah? E equals a half ME V squared. So that means the V will equal 2 times 10 to the 4 times E over ME root. Now, I'll just leave that for a moment. Then the electron will hit 3 protons and they move off together. So the momentum at the beginning is only from the electron. So that would be ME root 2 times 10 to the 4 times E over ME. And that must equal the momentum at the end.
Which is 3 MP.
Yeah, it'll be 3 MP plus ME
Times V2.
times, yeah, we'll just call it
Small v. Big V.
X. So the X is what I want when these 4 guys move off together. So the X will be ME over ME plus 3MP root 2 times 10 to the 4 times E over ME. Do you think you got it right? Can you retype this in? Let me see if you get the same answer. What's wrong, Gina? You don't look happy. Your answer's strange?
It's that is big.
It's a big answer?
I got 10,767.
Oh, that's pretty big.
Oh yeah.
10,000.
767.
So
10.8 times 10 to the power.
10.8 kilometers per second.
Mm.
Yeah.
Now, I know that seems large, but when we are talking about accelerated particles, these are the types of numbers or speeds that we measure in kilometers per second. Like, that's very fast. 10 kilometers in a second is the speed. You know. I think the particle accelerator in CERN, I think it gets particles up to 99% the speed of light. So it's big numbers. Is this okay, or is there a mistake? No? Is that what you got both ways? And Gina, you don't look too happy with this. You got this answer, Zach, when you typed in what I wrote, or?
Yeah. No, I didn't get the same answer.
Let's see.
forgot something.
I think
Forgot
that
the
E
ME.
should be ME.
I've forgotten ME.
Yeah.
So change the answer.
No, it's right. It's right. It's right. It's
Off
right.
by 1, yeah.
10.8 kilometers per second. Yeah.
Yeah.
Is that okay, guys?
Mm-hmm.
So what we'll do, we'll start the next lesson in a few minutes, but I'll let you try these for, we'll say 10 minutes, and then we'll start the next lesson. Okay? Not too difficult. Really, the only formula we're kind of using is this guy here. Is this okay, Lynn? Yeah. You need to write it down? You got it? Okay. We do magnets next, okay.